Welcome back. We're in the middle of exploring membership, and today we're going to try to explore membership when we are a little bit uncertain. This is part of a spectrum of possible memberships. We did a whole video on the possible memberships, which included classical membership, just true and false, as well as computational membership when you need real evidence, and then the realities of real life models, where membership is somewhere between possible and necessary. Today we're going to dig into how to make the possible and necessary much more computational. It feels a bit in tension. After all, if we can't really understand whether something is or is not a member, how can we rely on a computer program which is going to decide something precisely? The tension here will be resolved through something known as a crypt key model. The idea here will be to add some extra information to the membership test. So let's get into how this looks. So to summarize, here's what our test can do. In a situation where we have a bad website, in that case, we know that it's a bad website to start with, but there can be false positives. This means that the right logic to say here is that it's possible that the web is in the bad pages. That diamond stands for possible. There's a flip side to this. Suppose we take a test, we run a hash, and we end it with the filter, and it's not equal to the hash. In that case, we're guaranteed that we've never seen that web page on a negative list before. So we say that it's a necessary condition that the web page isn't bad. So now to get into the design of our browser, we'd like our users to have opportunities to control what risks they want to take. Maybe it's more of a nuisance for them to be constantly asked to approve of the websites. They might have a toggle switch somewhere where they can select one side or the other. They want to be on a good website with absolute requirements of passing a test, or they'll permit the occasional bad website so that they can use the web more easily. What they're doing is selecting which type of logic they want for the selector function, the characteristic function of the defined subset. Let's put in the modal logic. Over here, I have a good website must pass the filter test. The filter test is that chi of A equals falsity. In order that it must pass the test, that means we can't just have it simply be possible, it's necessary. That means a square. In this case, that would be the way to decide what isn't in the set. We must have this requirement. On the flip side over here, if we switch over the toggle to this more risky situation, we're adopting the view that maybe some good websites will get false positives. Maybe isn't the same as saying always. There will still be bad websites that are flagged as well. So when we flag something as chi of A equals true, we simply know that it's possibly a bad website. The possible truth of that statement is this version of the story. Now we see the makings of how we would actually program this. Set aside the mechanics of a toggle switch, what we really have is what's known as a state machine. It's basically a graph of dots and arrows. Each arc tells us where we can go, and they may or may not be labeled by the steps that let you transition from one place to another. To start out with, we need to recall a little bit about classical membership. Classical membership is when we decide that something is in or out and no middle ground. We call these membership tests true and false, and we often use the characteristic function chi as that test. Standing back to see this as a function, we create a new set, the set of allowable values that we could put into our chi test. What are the values of allowable strings A which will pass this test? That function starts with S and outputs true precisely for the values that lie in this subset. So if we were to articulate this with a commutative diagram, that means a flowchart where any two paths end up at the same place, we would fill it in like this. We would see that any value that lies in our target subset A would have evidence that's true for the chi test. Passing to the truth, then up to the set of truth or falsity, would only end up hitting the true values. Therefore, passing from this direction in the flowchart to just forget whether it's a part of the subset and applying membership all over again would result in the same value of true. This is simply articulating that chi of A is equal to true when little a is in the big set A. Now let's look at this computationally. While it's in our minds that we might be able to test whether something is or is not a member of our target subset A, we may not have that evidence when we're designing the program. The programming languages give us a lot of tools to build data types, but they don't give us the actual data that goes with the type. We have to design with the anticipation that later we will get evidence that tells us what to fill in. So what we do to solve this problem is we insert an intermediate block, a place right along this path, to stop our program design. Then later when data comes in, we might be able to take that data all the way to conclusions. So let's insert this step. So there we have it. I've inserted an intermediate place for our judgments to pause. Our original characteristic function is still living on the outside, taking any target string and assigning it a value of true or false. That would be the way of measuring whether whatever we want to talk about lives inside of this target subset. But with the computation in mind, we insert a precise predicate. The predicate took our strings and assigned them to a property or a proposition. This idea is to assign them not a specific value, but a data type, something that we can program the moment we're designing the algorithm. We don't know what the values will be, but we can make a storage spot for whatever the values might become, a place to make the judgments. For any checkbox that comes from this subset, we fill it in. That then gives us evidence to pass along to truth, and truth will eventually end up as truth. So if we follow the entire path, we'll start with our subset, end up checking off the box for the property that we can check computationally. This is what we actually programmed was the data type P of A. Checking it off was evidence that we actually constructed a member of that subset. Because these are commutative diagrams, when we are done with this picture, we are able to agree on the values of membership tests. Only now we have the opportunity to consider a computation. Inside of here are all the data types necessary to talk about this judgment. Whether or not we'll be able to judge will depend on the data we have and whether we have good algorithms to do it. Nevertheless, we are set up to describe this as a computational model. This has moved our classical set theory into our constructive set theory. So now let's switch back to our original question. We were interested in exploring when does membership testing allow us to discover that something is possibly a member, or necessarily a member, or the other way around. This added nuance of modality is something that we need to model real-life problems. How do we fit it into our picture here? What we'll need to do is update the possible values. No longer are we simply assuming that things are classically true and false. We'll now add to the narrative the idea of possibility and necessity of these values. So here's how we can begin to model these types of problems where we have necessity and possibility as part of the judgments we're trying to make about the membership of some element in a set. Once again, we think about the set membership as a function that takes in data from some larger place, subset S, and tries to judge whether that should be part of the subset A. So, once again, we simply write down the possibilities. Now here the possibilities start to include the different possible ways we could measure truth. We could have a necessary truth. We'll put a box with the T. We could have a possible truth. That's a diamond with a T. And likewise, we have necessary falsity and possible falsities as well. We can think of these now as ordered pairs. They have the standard classical true-false, but they've been amended by these modifiers, possibility and necessity, square for necessary, diamond for possibility. Now the key thing is to update our chi test to match that. We can see now that we can mimic the diagrams we've used before for our constructed membership of sets. Only now we've amended the possible outputs to not just be truth and falsity, but to also have these modifiers of possibility and necessity. However, this leaves some new questions. What is it that we consider to be a value that is valid? When we have chi of A for some string A, we want to make sure that that's in the subset A, according to whatever rule is appropriate for our study. Are we accepting necessary truth, or are we also allowing possible truth? Which one is the right one for your situation depends on the mode you're in. We want to be able to update the story of membership based on these different modes, and therefore we have possible choices. They'll depend on what state we're in. Let's put in some of the options. This would be indicating that we only want to accept the values in A that are necessarily true, no false positives. By flipping the square to a diamond, I change from necessary truth to possible truth. With a possible truth, I retain the same membership as before. Any place that is necessarily true is guaranteed to be in there. However, I now also include the possibility of some false positives into my model. I'm being more relaxed about what gets in because for this scenario, that's okay. With the addition of the necessity and possibility symbols, we are able to incorporate the notion of subsets that recognize whether they are in or out based on the kind of modality we're interested in studying. But we still haven't told our computer how to judge the change in possible states. How do we know if something has moved from the possible to the necessary? How do we make a judgment? Let's add that to the story with the inclusion of a state machine. So how can we implement these semantics? What I have behind me is a picture to illustrate what's going on. We have two different types of membership tests based on the mode that we're in. This could appear in your browser as a simple toggle switch. What's hiding behind there is a state machine. So let's walk through the process. Let's assume that the green setting is that a good website must pass the filter in order for the browser to direct you directly without a warning. What we'd say in modal logic is that it's necessary that the chi test is false. Remember, our chi test is deciding whether a website is on the naughty list. So we should be false if we're going to pass the filter. This test might be too aggressive. It might send too many warnings to the user, and at some point they may wish to turn it off. By selecting the red mode, they transition to a new state. In this case, we would change to the diamond, meaning it's possible that chi of A equals false. We wouldn't know for sure. At this point, we can see that we're drawing a picture that changes what subsets we think of as the websites we can browse without a warning. Notice the arrows I've drawn are indicating the changes in modality, the changes in state. If I'm already in the green setting and I apply the green toggle, I just simply stay where I'm at. And if I've moved to the red setting and I apply the red toggle, I stay where that's at. But I have the ability to flip between them. It is said that I'm changing the state of the state machine. I think of myself as living like a player on a board game that moves between squares, based on what they roll, the selections they make. The way this affects my subset is in what I'm choosing. If we were to draw the pullback diagram that classifies our subset, we now see where we would put in these modalities. We're simply selecting how to interpret the chi function by adding in this possibility or necessity, and we're changing whether we want the false or the true values, whether we want to focus on good websites or bad websites, false positives or false negatives, or somewhere in between. There are many more modes you could consider and many more diagrams. These diagrams are an enormously useful addition to the logic that we normally look at as first-order logic. They clarify that sometimes we need to think about a change in the logic we have simply by modifying the semantics, that is, whether we think it's possible or necessary. This diagram language has a special name. In mathematics, it's known as a directed graph. In logic, these are known as possible worlds, or Kripke semantics, after Saul Kripke, who invented them. In computation, they're known as state machines. Whichever way you approach this, the key idea is to keep track of the fact that we're adding extra modifiers to the values of truth and falsity. Whether it's necessary, possible, occurs in certain times or in certain places, these modalities are reality. They give us the granularity to explain truth and falsity in a way that accepts that reality is sometimes going to change those meanings by adding words that qualify it. And they allow us to be more precise about the logic we're exploring and create data structures that capture that notion as well, simply by modifying and extending our characteristic functions and their associated predicates. The result is we can now start to talk about the realities of data in a computationally feasible way, which simply builds on our classical understanding from before. Until next time. That's how you take care of your chalkboard.